question totally right. And I have to. Which one did you get right? 2.
Yeah, I was like, you know, off today. The last time I was off was the day before. And, that's when they talk about that's right.
Morning. Morning. One question. Video. Your flash videos. The tech flash technology. Okay. Just getting somewhat difficult because it's not supported like it was by the Adobe Corporation. And that more and more graphics are not taking on. Oh, okay. Yeah, we're just getting the since we've got our work set, are they being used as guys today?
Yes. I created a couple of them years ago.
Yeah. And the technology that made that, it was Flash, Adobe Flash, okay? So our work set, your work set, have hours for this semester. People not having to create those videos. Is that okay? I'll pick it out. Because, and that, because I tried, we're looking at trying to get them to play on mobile devices better. And that technology, iPads, iPhones don't take much at all. Okay, unless you buy on this package. Okay, so I'll talk to them tomorrow, and then we'll get them access to video. See. And I've got out of the situation that I have it to be played in full screen. That's not cool. And you want it out there, I guess that yeah, just fine. And we try to keep it all set to my will. And I hope
Some of those,
I just want to picture we're not breaking any copyright issues. Okay.
It smells like stink bugs up here.
I know it does. I'm guessing. Sorry, Chad.
Oh, I don't want it.
I'll have to bring my originals tomorrow.
No, this isn't the worst I've done.
This is probably the worst I've done.
Really?
I think so. Yeah, I haven't even calculated it yet.
See, when I walked out of the test, I felt pretty good about it.
And then
grades
it
still
goes to
dropped.
grades.
Yeah.
And I was like, what the heck?
But this is one of the better grades I've had.
Why are you shutting the door
You're right, I'm just kind of late and then shutting the door.
Man, I was expecting, since I got here so late, for everyone to already be in here. And then when I saw Carson, I was like, oh no, I am late. He's here. Because I know you're always late. And then I was like, when I came up here and all I saw was Chloe was here, But time to figure out what I actually got.
I got number 2 completely right. So if you need that one, I got you. That's it though.
At least. I got 1 point off of number 2. Oh my goodness.
There you go.
How's that enough to be so low?
Okay. The only thing you marked wrong was my actual answer. All I needed was that.
Exact value you wrote, but that's
Right.
fine.
I was so
What
close.
did you guys get for free?
Oh, I'm completely right.
What'd you get?
I got 8.
Just 8?
If you'd like to see.
I'd love to see it.
Step too far.
I like the fact that he gave us a graph so we could rectangles.
Oh. That was stupid. Sorry, not yours.
It makes
When
me
I get
happy
one
when
wrong,
I
he
get.
just puts a bunch of question marks.
Yeah.
I like when I get full credit on it because that's just one less I have to do on corrections.
So it's just plain old late.
One of the times that we did corrections and I got some of the stuff completely right, I was so in the habit of having to rework everything that I reworked the ones that I got right.
Yeah, another lesson plan.
Okay. Yes, I got another one.
Alright,
Did anyone get number 5 right?
I
Alright.
probably a little right.
It's gonna be like the
I got half the
Be
credit.
like next week.
I got 6
I'm
points.
ready to never have to.
What did you get for your final answer?
I got negative 76, but I don't even know why I got 6 points because I did, instead of doing the midpoint sum, I did the max sum. How it's like on the next page and we've got these 2 different things, and so that's what I did, and that's wrong. But, oh well.
I thought M was midpoint.
It is midpoint. I did the wrong one.
Oh.
So give me 6 points, so I'm just.
I did the right one and he only gave me 5. But he didn't mark any of my work wrong. Did I just add wrong? I don't know. I'll have to check back over my work. Oh man, I didn't round to the thousandth. That's it.
Come on, Sandy.
That's it. Why? Okay. Well, on the bright side, a lot of these reworks are probably going to be fairly simple.
On the bright side, we have like 2 weeks left. We have like 9 days left.
And then I didn't get number 11 or 12.
Then I can focus on real things.
Refer to graph. I thought that was a pretty solid explanation. Okay.
What, for number 12B? I had a great explanation for that.
Okay.
Let's deal with that stuff you did.
I was just glad we took the test before break so we didn't have to worry about it when we got back.
I wish we'd taken the test after break.
I had enough to work. Yeah.
So we have more than 8 days ready for each.
But if we had after Thanksgiving break, I would have never slept. Did about as good as
Amanda,
Yes.
you, like I can't see Sammy. Can you change the point of the camera a little bit?
Sure.
I can see Sammy's hand. Maybe zoom out a little bit. There you go. Great, thank you. Hey, Sammy. right, now we can see it. Everyone have a nice holiday break? Eat too much?
I always eat too much.
Are they making any Black Friday big purchases?
I'll save mine for Cyber Monday, so.
Across the county, we made one shopping stop at Washburn store on Friday. You up in my just because of we're there, you know, we're out by that. Okay, so Chevy test track. Well, I thought that's good. Couple quick comments, I guess, on numbers 8, 9, and 10. Since those all three were related together, did 8 incorrectly. I tried to follow what you did from that on number 9 and number 10. If you correctly used your number 8 result on number 9 and number 10, then I gave you credit, but you'll still have to redo it because it's wrong because you're number 8. A couple people I even pointed out, like on number 10, I showed that the reason they didn't get full credit on number 10 because what they did with their number 8 was wrong, but then they also didn't do number 10 correctly with their number 8. So my caution is, if you have to redo those, make sure you don't just copy what's there. Like if I remember a couple people I showed, well, here's the answer you should have gotten with your number 8 in number 10. But that's not the right answer. That's just what you should have done had you done your number 10 correct with your number 8. And so, again, if you're redoing 8, 9, and 10, make sure you redo them from the beginning and don't just copy them. Okay. Number 11, part B, several people, a lot of people, made a error that went like this. I guess I'll write it on the left here. So, interval 1 to 5, 2x plus 3. Most everyone recognized that you could rewrite this as 2 times interval 1 to 5 of f of x. But then this next part right here, this 3, what do I do with that? Some people mistakenly said, well, that's just a 3. You just put a 3 there. But that's not true. The property is the sum rule, and this should become an interval from 1 to 5 of 3 dx, like that. And that means you have to actually compute that interval. Now, there's a couple ways to do that, folks. You can set up a right sum, limit n goes to infinity, and use this as your function, and set up a right sum and calculate that. Or you can use geometry. Because this is just a function. What's that function look like? Horizontal line. From 1 to 5, a horizontal line. Can you calculate the area under that fairly easily? Yes. So that was a mistake a lot of people made. It's just viewing that 3 as just a 3 rather than an interval of 3. That interval of. Be careful there. Go through the big comments. Any questions on the test? Yeah, I think, yeah, it's spelled correct, sure.
Yeah, when's this due? Oh, actually, that reminds that one bigger thing. That isn't gonna, we're not gonna get. When is it due?
Yeah, yes, Josh, question?
Question, when is the reworks due for this block test?
That's a good question. Let's say it's due on Monday.
Yes.
Woo!
A whole week to get it done. That way,
Oh, yeah.
other questions about the test? Anyone? All right. Everyone's rested, ready to make that last sprint around that last curve or come around that last curve towards the finish line. We don't want to start walking now. We're gonna kick it into a sprint. 3 weeks total remaining, 2 weeks of which we'll dedicate to this next block material and its test. And then the last week of class, we'll have 2 days of final exam, 2 days of review for final. Now, review for final exam, just so you know, that's if you have questions, we'll go over. There's no way I can come in here and reteach the entire calculus in 2 days. So, I can test or whatever you want. We can talk about whatever you want if you have questions. Talk about that later. For now, let's go ahead and so block 9 is the last block of material. And in it, we're going to eventually, not today, but in the very near future, we're going to cover what's called the fundamental theorem of calculus. So the fundamental theorem of calculus is probably kind of a big. But today, we're not quite there yet. We have different kind of interval. Last time, I guess I'll start here. As we introduce this next topic, let's review what we've already covered real quick because there's a relationship between the two. We need to know this, understand the two different things and the different relations we had previously. We had a definite interval. Let's review what that was. So it's like if f of x is defined on the interval a to b, then find the definite interval from a to b of f of x. X was defined as remember, this was just test on, so this is a review right now. Since we have a holiday, so it's good to review this because it's been, we ate a lot of turkey and dressing and stuff. So, what's the definition?
The limit as n approaches infinity of the sum of k equals 1 to the n of f of x sub k star dx.
What else is required as part of this definition?
Equals B minus A over N.
So that was the definition of definite interval. It is this part right here without the limit. What do we call this part? This part of the definition of a definite interval. What do we call that? What was it named? Riemann sum, named after a German mathematician, Riemann. So Riemann sum, and then we did the limit of the Riemann sum as n goes to infinity. That was the definition of what we call a definite interval. And it calculated what did it result in? And if we don't approximate, then it's exact. If we have to approximate it, we can't. So that's what we've covered previously. Now today, we're going to define a new object called an indefinite. So if f of x is continuous, then we will define a new symbol. Also has the elongated s just like the definite interval, but instead of having an a and b limits, it has no a and b limits on it. So it looks, I haven't defined it yet, but just notationally, this symbol looks very much like that symbol. They're not identical. There's a straight between the two of them. And definite interval looks very much like definite, except for it's missing the A and B subscript and superscript. This is defined as okay, so an indefinite interval is defined this way. If f of x, function f of x is continuous, then we define this symbol called this the indefinite interval of f of x with respect to x is defined as a new function called capital F of x and then plus a constant c. C is an arbitrary constant. Where f prime of x, capital F prime of x, is equal to little f of x. So, in effect, what we're creating here is the family of antiderivatives that we've discussed previously.
Yo, we get
here. So, the output of this operation as opposed to that operation. This output is not signed area. It is a function plus any constant where this function's derivative is the original function. So we're creating, instead of an area under a curve, this is simply creating family of antiderivatives. the two different types of interval. One's called definite interval, one's called indefinite interval. One is calculating a number called the signed area. One is calculating a function, like a family of functions. Okay, we've done this a little bit before, so this is just kind of formalizing our thought process somewhat. We can now generate some formulas. We can calculate some. Let's do one real quick. Let's see. What would be the indefinite interval of let's find what that. The integral is an indefinite interval rather than a definite. So we want this time not an area, but a function. So its derivative is the cosine of x. So what does this equal? And we add a plus c constant. How did we know that? How were we able to come up with this? You have to go back to what you learned before about derivatives. The derivative with respect to x of sine of x is equal to cosine of x. Also note, folks, the plus c seems like lessons like, why do I have this plus c? Why, we've talked about it before. We'll go over it again in just a minute why that's there. But let me just emphasize one thing. What is the derivative of a constant? If that c was, say, 4, what would be the derivative of that constant? 0. So you would still just get cosine of x here. That constant doesn't affect the derivative, so it's included because it's a family of curves. And we'll need to look at that one more time. So let's take a look at a little more detail about why we got the c there. So we just did one quick example. Do some more here in a moment. Let's see. Let's suppose I give you a function now and graph one. So this is f of x. Let's call it a prime. So if I wanted to find the function f of x that goes with it, the antiderivative function, what we did previously is we created a slope field.
Oh, yeah.
Now I'm trying to create f of x as a function graph. And the way we did it was we created a slope field. Y'all remember doing slope fields? So I look at this function f prime of x, and for example, right there, it tells me the slope is 0. So at that location, I have slopes of 0. So I make a slope field with horizontal tangent lines. Also at that location, I have slopes of 0. So I make a slope field with horizontal tangent lines. What else do we know? Yeah, out here the slope is below the axis, so it's negative, so I got to put some negative slopes out here. Out here it's negative, so I got to put some negative slopes in between the two zeros, I got positive slope, and it's more positive and then less positive. So I'll start off with slightly positive slope. And then steeper slope, positive slope. And then over here, less is still positive, but less positive slope. So I'll come back to slightly positive. Now we can pick a spot and start graphing. So if I started, say, right here, I would touch the tangent lines. I might get a graph like that. But the point is, it doesn't matter where I start, they'll be parallel. I can start, say, here. And I get, well, you get the idea, but there'll be a family of parallel curves. So what I'm saying here is that I start with f prime of x. I do the indefinite integral of f prime of x with respect to x. I get this family of curves. So we've done that before. We've talked about it before. Now we've just formalized it. We've given it a special name. We've given it the name indefinite interval. But the concept is no different than we've discussed before. Now, again, it's a little confusing because you're using this very similar symbols for two different types of intervals. Again, when we get to the fundamental theorem of calculus, we'll tie these together in a very special way, which is why they have similar names and similar symbols. But again, the meaning is very different for the two different types of intervals. One is area, one is a family of anti-derivative functions. Okay, so in the book, there's some theorems we need to just real quickly scan over. I don't think they're too challenging. So I'm on page 354, section 4.4. Theorem 4.14 at the bottom of page 354 says if f and g are differential functions, then f prime is equal to g prime if and only if g of x equals f of x plus c. Does that make any sense?
Yeah, I get it.
So yeah, the only way your derivative can be equal is if the antiderivatives differ only by a constant. And the c that we're talking about, so the distance between any 2 points here, that distance right there, that's my c between the two functions. But they have equal, they both come from the same derivative. They both have the same derivative function. So I mean, that's a fairly obvious theorem. We already covered the indefinite interval definition, so we don't need to cover that again. Now, power functions. Let's talk about that. So like we just did here with a simple example, what do you think about antiderivative of x? Respect to x. And it's going to be equal to something, again, plus c. But let's start thinking backwards first. Think backwards. Derivative of what function will give you x? This could be a game of guess and check if you wanted. I mean, y'all realize derivative of x squared is 2x. Notice how the power of the x is a degree 1, like we want here. But I wanted a 1x, not a 2x. So if I put a 1/2 x squared, 1/2 is a constant, so you can pull it out in front, and then the derivative of x squared is 2x, and those twos cancel, which gives me an x. So the derivative of 1/2 x squared with respect to x is x. Therefore, the antiderivative of x is 1/2 of x squared plus c. One more real quick one, just practice, and then we'll write down the prompt rule. Will be the antiderivative of x squared. We're looking for the indefinite integral of x squared with respect to x, which is looking for the antiderivative of x squared. Well, that's 1/3 x cubed plus c, because what? So yes, and that leads us to the rule.
Oh my gosh.
So definite integral of x to the n with respect to x is equal to what do you might have a thought based on what we've seen so far? And think about the pattern of how the derivatives work and how the antiderivatives work. Okay, so let's review. Let's get down here, because the derivative of x to the n is equal. What is the derivative of x? Let's remind ourselves of that. Remember this basic power rule? Well, if you're going to go the other direction, what do you think? This one is multiplied by the original exponent, and then you reduce the exponent by 1. We proved that, I think. But what do you think if you're going to reverse it? You're doing the antiderivative. You're going in reverse. You're going the opposite direction. So what do you think you're going to do? Jacob said something about division. I agree. Instead of multiply, we're going to divide. But what else? You're going to go up in power instead of down in power. That's right. So this is going to be 1 over n plus 1 times x to the n plus 1.
Mm-hmm.
Check it right here. N is 2, this example, n is 2. And then 1 over 2 plus 1 is 1 over 3. And then x to the n plus 1 is x to the 3. So that rule seems to work. I have one concern, though. Okay, so in this rule for derivatives, there's no real issue. So I multiply.
Mm-hmm.
Now I'm dividing. Can you think of an n value that might be a problem with this rule?
-1.
n was -1, we got a problem. So this rule is only true part of the time. So this will be true if n is not -1. So what do you think about when n is -1? So let's remind ourselves, what did we deal with before when we had a -1 exponent for n or something, or a derivative? Think about that. Derivative of something is x to the -1. That's the issue right there, folks. We're stuck on that -1, so I'm asking you now to think back to derivative. Derivative of what gave you x to the -1? Well, if you don't recognize it right away, what's another way of writing x to the -1?
What, 1 over x?
Over x. How do you recognize?
Nope.
It's the ln function.
Oh my gosh.
The x derivative is 1 over x.
Wonderful.
Okay, we see this? So back over here, going in reverse is going to be the natural log of x, but we have one special extra piece of information we have to include. I'll even write it in red to emphasize it.
Absolute value.
Don't do this to me, Dale. No.
So, definite interval of x to the -1 will be the natural log of absolute value of x. Why, oh why do we have to have absolute value on there when we didn't on anything else?
Because natural logs can't be negative.
The x value, the input to natural log can't be negative.
Yeah.
Natural log value, so yes,
That's what
you can't have an input, a negative value for logarithm. And x to the -1 could have a negative value. So it's a domain issue. Domain of x to the -1 is everything but 0. The domain of logarithm is everything positive, greater than 0. So we have to be careful that we restrict the domain to be satisfactory for the logarithm. Okay. I think it's pretty straight up.
Straight up.
But what if it wasn't just as simple as what we just did there? Go back over here.
Por eso you.
We've got some rules that we can apply. Let's skip a page until we get to the discussion. On page 357, the constant multiple and the sum rule. Just like with definite intervals, indefinite intervals have two generic rules we can talk about. So the multiple rule works just like it has done for everything else. The indefinite interval of a constant times a function is the same constant times its antiderivative. So, like we've done on limits, like we've done on definite intervals and derivatives, now on indefinite intervals, constant multiplier can be handled separately and just multiply after that. Same thing for the sum rule. So the indefinite interval of the sum of two functions can be handled as two separate indefinite intervals, added together after that. how about an example?
Yeah, I'm fine. Just thinking about my live stream that I'm gonna do at the end of the month.
So indefinite interval 4x squared minus 3 sine of x.
Looks pretty good to me.
We write this as 4 times indefinite interval x squared minus 3 times indefinite interval of sine of x. What is the indefinite interval antiderivative of x squared?
Dang, he won.
What is the indefinite interval or the antiderivative of sine of x? Negative cosine of x. Why negative cosine of x? Well, follow that. Negative cosine of x is the antiderivative because the derivative of simply cosine of x is negative sine. So to get a positive sign here, we've got the negative. So this becomes 4/3 x cubed plus 3 cosine of x plus.
I dig it.
Okay, some other special rules that we should be aware of, that we should recognize fairly quickly and easily. Besides sine and cosine, other trig rules that we've seen before. In terms of derivatives, we could identify
The hind rule.
antiderivatives.
Hind.
So we'll just review those real quick. Let's see. Because the derivative of sine of x equals cosine of x, then we get the indefinite interval of
Is that the case?
cosine of x is sine of x. And because the derivative with respect to x of cosine of x is negative sine of x,
Okay.
and the indefinite interval of sine of x is negative cosine of x.
Mr. Gaddis,
That's a question.
just a minute ago you said that the derivative of sine of x is negative cosine of x.
Did I say that?
Yeah.
No.
Yeah, that's what
Yeah,
he
it's
wrote.
the opposite. It's the other way around. Yeah, it's
Oh,
backwards.
it
How about right here, Rachel?
Yeah.
I didn't say the derivative, I said the antiderivative of sine of x.
Okay. The antiderivative.
Okay. Indefinite interval is an antiderivative, opposite derivative.
All right.
So just like right here, so I just said right here, derivative, because the derivative of cosine of x is negative sine of x, you learned that long ago,
Mm-hmm.
and the antiderivative of sine of x is the negative of cosine of x. Meaning I can move this, I can multiply both sides of this equality by negative, and I would have the antiderivative now of sine is negative cosine.
All right.
Thing is, at this stage of the game, there's not a lot else, but for example, we know the derivative of tangent of x is what? Secant squared of x. That means the indefinite interval or the antiderivative of secant squared of x is tangent of x. Comment to you real quick. We'll learn in Calc 2 some techniques for determining the antiderivative of secant of x. This is the antiderivative of secant squared of x because we know a direct derivative from tangent to secant squared. We can do a direct antiderivative from secant squared of tangent. But think for a moment, did we see a derivative? Think about this. Can you think of, it gives me an answer of secant of x like that? No, we didn't see one like that. So going from this side back, it's a little more troublesome. So that takes some more techniques that we haven't covered yet. Other ones that we've seen derivatives of that we can now write an antiderivative. The derivative of secant of x was secant of x times tangent of x. So once again, I can go backwards and say the antiderivative of secant of x times tangent of x with respect to x is secant of x. And similar with cosecant and cotangent, I mean, I think we got that. Right? I mean, the derivative of cotangent of x is equal to negative cosecant squared of x. So I can do the indefinite interval of cosecant squared of x is equal to negative cotangent of x. And I could do derivative of cosecant of x, we learned was negative cosecant of x times cotangent of x. And therefore, the indefinite interval of cosecant of x times cotangent of x is the negative of cosecant of x. So your basic trig rules. What about your inverse trig rules? We learned some of those as well. Probably the most popular one that we learned was derivative of inverse tangent of x. I remember that one yet? 4 plus x squared. And it's 1 over 1 plus x squared, like that. So that means the antiderivative of 1 over 1 plus x squared is equal to inverse tangent of x plus. And you got on this page here, you got for inverse sine, inverse secant as well. You remember those? Derivative with respect to x of inverse sine of x is 1 over the square root of 1 minus x squared. We went through and derived that some time ago. I don't know if you remember how we did that. Because we might have an example. We did this with implicit differentiation.
Mm-hmm.
Anyways, so this yields for me the indefinite interval of 1 over the square root of 1 minus x squared over sine x. And then I guess secant inverse, so derivative of secant inverse of x is 1 over absolute x times root of x squared minus 1. And so, therefore, the indefinite interval of 1 over absolute x times root of x squared minus 1 x is okay, so those are the basic ones that we can discuss and do. Oh, let's do the exercise. Then we just have special cases. Okay? What's the derivative of e to the x? I remember the derivative of e to the x.
Oh, yeah.
Called the natural base because it's the only function in the world whose derivative is itself. And the antiderivative of indefinite interval of e to the x and not to be outdone, what about any other base besides the natural base, like b to the x? X times natural log of b.
Yeah.
The derivative. So if I divide both sides of this equality by natural log of b, then I can say that the indefinite interval of b to the x with respect to x is equal to 1 over natural log of b times b to the x. Let's see. Okay. Let's try some examples. The others on page 357 are hyperbolic. Again, we didn't cover hyperbolic, so that will be tested on. Let's try a couple of examples. And I want to mention also the special cases on page 358. There's some special applications of the product, quotient, and chain rules. Let me do those couple first, and then we'll do 4 examples. Okay, so page 358, I'm not going to write all this out, but hopefully it makes sense. The first rule on top of page 358 says the indefinite interval of a big group of f prime times g plus f times g prime, all with respect to x. You recognize that as being the derivative of a product.
Yeah.
Well, therefore, the antiderivative is just simply the product, f times g plus a constant. And then the second rule is the indefinite interval of a big quotient. But you should recognize that quotient as being the applied quotient rule. So if you anti-differentiate the quotient rule, you should get the quotient f times 3x plus c. And then the last one is the chain rule. F prime of g of x times g prime of x. Y'all remember the chain rule? Did you read that?
The high rule.
Besides that, you can undo the chain rule as f of g of x plus c. Try examples here.
You can get a 20-minute nap. Go back.
Yes.
Obsessed over results.
It's not obsession. It's admiration.
Exactly.
Oh no.
I know
It's
this.
the quotient.
It's a quotient rule.
It's like a quotient rule, I agree. And at this stage, it's a matter of recognizing that it looks like a quotient rule, and then trying to guess and check what the original quotient was from which it came.
Well, I'll tell you what. The g of x is ln x because it's on the bottom being squared. So I can tell you that much.
You know, we got an ln of x in the bottom, I agree. This
Got him.
quotient rule has a square at the denominator.
Yeah.
So we got the denominator gets used, you know, this is f prime times g minus f times.
It's x squared on.
2x.
No, it's x squared on top. Come on, man. Come on, man.
Well,
Squared.
if f
Please.
of x is x squared, the derivative is x. That seems like it works. But what about this term here?
Oh crap.
Well, you
X squared
have x
times
squared over x because that's the derivative of the natural
Oh
log.
my gosh, Sammy, you're so smart.
Yes. So this is f prime. This is g.
Oh
This
my
has
gosh.
to be f times prime. Well, if g is ln of x, the derivative of ln of x is 1 over x, and 1 over x times x squared, we said, makes x. Yeah, this is just x squared.
Oh my gosh. Y'all are
Else
champions.
that works. So f is x squared, g equals ln of x, and the quotient rule is it. Okay.
Got him.
How about another example?
I actually appreciate these examples. I feel like we're gonna need a test.
I like this. Well, just give it some time. You will.
Oh, no, there's a free. I'd rather not do this.
Let's see. 2x plus 1.
Yes, you can.
Wouldn't that just be?
The indefinite interval of x times e to the x squared plus 5.
You just
I'll tell you what.
use 2 to the x squared plus
Have you
1.
Is that a constant I see in the run?
That would just be e to the x squared plus 5 plus c, right?
That's just a chain rule.
Oh, it's a time rule.
no.
Of e to the x squared plus 5 is what? Going back to derivative.
2x.
This is my final answer. 2 I was right at you.
Just 2x.
Times
2x.
that
Oh my gosh.
a chain rule of the 2x. So this is just derivative of that.
Oh.
This
Wow.
is just e to the x squared plus 5 plus c.
So stupid.
Okay. There is another little small issue we need to deal with. I think we may have talked about this before.
Third hour, yes.
What do you think? trying to find the definite interval of cosine of 3x with respect
It's
to
gonna be.
x.
The chain rule, right?
This doesn't look like a chine to me. Is it a chine?
So yes.
Just. Oh my
derivative
gosh.
of- but, I mean, what do you think it relates to? Derivative of what is going to be cosine?
Negative
Oh.
sign.
Oh my
So
gosh.
you think it should be the sine of x or the sine of 3x?
Why would it be negative sign?
Please tell me it's 3x. Please. Please. Thank you.
What is the derivative of sine of 3x?
Cosine.
Negative. Oh.
Cosine of 3x times the derivative of 3x.
Which is 3.
So
3
one.
cosine of 3x. But the derivative of 3x is just a 3.
So wouldn't our function have a 1/3 effect?
Perhaps.
So if I divide both sides of this equality by the 3 that you see right there,
So it'd be 1/3 sine.
you would have a 1/3 in this, and that would, I think that would do it. This is apparently 1/3 of the sine of 3x. You know, I'm switching directions on my derivative to antiderivative. I want to go from here back to this, but I got to divide by that 3. That was easy. Questions on that?
No, I'm good. Got him good.
Yeah.
Oh yeah. You know what this looks like? This is looking like a tan to me.
Wow.
Come on. Come on.
More
give it
with
to me.
the same type of thinking, then I want to ask us to look at something else. What do you think on this one?
It's looking like a tan.
Inverse tangent, that's right, related inverse tangent.
That's what I meant.
So,
Because of the.
It's weird to memorize that.
Yep.
I mean,
we know the derivative of inverse tangent is 1/1 plus x squared. So that one looks a lot like that, I agree. But
yeah.
it's not x squared, it's 4x squared. So what do you think we should put in here instead of just a simple x? What should we put in here?
4x.
Is it 4x? Like
I heard of
thorax.
4x. Okay, let's try 4x. That's 1/1 plus 4x squared times the derivative of 4x. Which is 4/1 plus 16x squared. So that's an improvement. We don't have just a simple 1 plus x squared. But that's not quite right there. Now, I could divide this 4 to the other side, and that would take care of the 4 in the numerator. But that 16 is not quite right. So what else can we do instead of the 4 there? Put this as a 2.
It's a blast thinking right there,
That
bro.
would be a 2. This would be a 2.
Dang.
And 4, and that would be a 2.
Still not there.
So now, we got 1 plus 4x squared, that's right. We got a 2 in the numerator, so if we divided by the 2 on both sides, we could get 1/2 of inverse tangent of 2x.
Got him.
This 2 here, let's try it, y'all. Go with me.
Got him good.
I just want to do that 2. I can rewrite this as derivative of 1/2 of inverse tangent of 2x is equal to, and I've divided that 2 over to here, so this is just 1/1 plus 4x squared. So now I've got something that looks just like that, so I can just undo it. Okay. The homework you're supposed to look at on Moodle section 4.4. In the last couple of minutes, I want you to ask you to go ahead and look at problem, like 3 minutes, problem 16. It's one of the assignments on page 362, or 362, or 16.
good.
This was on a previous test. Essentially, we had a y. I think it was on the test just got back. Y is the definite integral of f of x times g of x not equal to the product of two definite integrals. Well, that had to do with the sums and products of sums and things. But now we're doing indefinite integral. And number 16 is a quotient, which is 17 is a product. But it again doesn't work the way you might think. It's not true in general. And they're asking you to come up with two functions, f of x and g of x, so that it's not true.
I got one. F of x
Real quick, see if you can come up with something. Take a minute or two, and you want to identify an f of x. Tell me what that is. Tell me what g of x is. Almost anything will work, but just see if you can come up with something. So that the indefinite integral of the ratio f over g as a single entity is not equal to, in general, the indefinite integral of the numerator by the indefinite integral of the denominator. And there might be one or two cases you can find that do work. Can you find an example? You can find one example that doesn't work, and it's not a general statement you can make.
Okay, this
Can you
one's
find an example? Give me a function. Yeah.
okay.
Keep it
F
simple.
of x is going to be
Almost everything does not work. You'd have to really try hard to find something that does work.
This is going to be 1 of x. Got him. Got him good.
Simple function. X is 1, okay. Name me another simple function.
2. Come on,
X
2.
is 2. Okay.
Yeah.
Let's see if that does not work, okay? So what's the indefinite integral of 1 over 2? What is that going to be?
Just
I'll let you mull on that for a minute.
Don't do this to me, Dale. Don't do this to me.
That side's going to turn into 1/2 when it's all said and done.
So it goes in front, but then you take the indefinite integral.
I need a function whose antiderivative, so I'm looking for a function whose derivative is 1.
X.
Yeah,
X.
It's x.
Yes, X.
I need a function whose derivative is 2.
2x.
2x.
I have been blessed.
I need a function whose derivative is 1/2.
1/2 x.
Is
Yes.
2 equal?
no.
No. Those x's cancel. So 1/2 and 1/2 x are not equal to each
Wait
other
a second.
unless
Oh.
x is 1.
Stress out. I thought they were equal.
One has an x and one doesn't.
That gives you something to think about. Remember, the derivative of power of x to the 1 power, the x goes away, you just get the coefficient. So antiderivative is something that power. All right, so do some homework tonight. See you tomorrow. Hopefully, lots of questions. Practice on these antiderivatives.
All right, let's go to my Kia. Should we home? Should we home dishwasher?
Dale.
Wait,
Sammy, didn't your dishwasher break?
Yeah. I'm trying to take something out of it so they can wash it. And it broke.
I'm gonna call the
Nice.
Dale washer.
Okay, we got it to the point where now we can wash one rack at a time.
This
Okay.
About linguistics.
That's everything.
I don't know.
Probably.
As long as
Wait,
laughing.
so do you want to put the whole
No. I'll do it in a second. I'm gonna put on my clout coat
What was
first.
terrible was I got home and my parents were like, we wrote the dishes. She was like, you gotta be kidding me. That's a lame excuse.
Turns out if you do your homework, you get done.
Wow.
How about that?
You actually do the homework?
No, I do. And it's in my grade.
Yep. It's Thursday.
I just want to make an A so I never have to take math again.
Whatever, you're gonna take math again if you're going into medicine.
Yeah. Gotta take that stats. Oh wait, I'm taking stats next semester.
Are you?
I'm taking a break.
It's a different.
Math.
It's a lot more words.
Yeah, I like words.
You did good on your test.
My other